All right. So last week we talked about data transform. There are a couple of concepts we're going to cover today, and then we will going to change. So we're going to do something deeper in the data transformation. Talk about how something like TensorFlow Transform works with Apache Beam under the hood. So in idea again, that TF transform, PyTorch transform, they all have a pipeline similar to this. There's some data comes through. You have a transform library. Transform data, they have some sort of like a trainer, TF trainer, PT trainer. They give you a model and you serve that. All of this happens, what you see on the bottom says pipeline plus metadata storage. We're going to today also focus on the metadata. But for now, just assume that there is a storage that you store some metadata in. And we have seen this before, again, in TFX or TensorFlow Extended. This is the pipeline that you have. Now, under the hood, the TF transform, the one on the bottom, which is responsible for data transformation, has something like this, basically. So data comes as part of the example gen, which is a library responsible for reading your data. And you have that schema gen, which was responsible for creating a schema and statistics basically from the training data. And then you have that transform. Transform is technically where your code will sit. Otherwise, the example gen and the schema gen is something that's already provided, but transform is basically where your code will sit. The result of the transform is something called transform graph. And that's basically, it builds a transformation graph that you can reuse it later. Now, and then you also get the transform data. The way that works, it's something like this. So on top left, you have raw data. When you work with, again, TensorFlow transform, PyTorch transform, for example, similar concept. The raw data, in TFT at least, goes to Apache Beam. It's under the hood has the Apache Beam. Apache Beam basically that TF.transform API. What it does, it produces two things. It basically returns you a graph of that transformation and basically converted or pre-processed data. So what you see as the output of the Apache Beam is the TFT TensorFlow graph, and then it's the process data. And then when you work with, for example, TensorFlow training, the result of that is also two things, a model and basically a graph. Now, when you want to serve this, so this pipeline that you have, when you want to use it for serving, when the raw data comes, the only thing you need is that TF transform graph. So you don't need basically any other code for data pre-processing if you have embedded as graph concept. And that's all you will need. So the raw data goes to the same graph that you generated by Apache Beam or TFT. And from there, it goes to the model that you generated by basically TensorFlow trainer. And then you can make a prediction. What's the benefit of something like this is, if you do something like that, you don't have code divergence. That means you develop a code in one language or in one environment, and you need to convert it for another environment. So this has some benefits. Now, if we go one level deeper in TensorFlow, and again, this is TensorFlow transform, what happens within that graph, you basically see something like this. How many of you have seen TensorFlow or TensorBoard? All right, not many. Okay, I highly recommend you to at least look at the demo of TensorBoard to just get some sense of how does it work. But so here, what you're seeing, TensorFlow transform has something called analyzer. Analyzer are mean, standard deviation, quantiles, and stuff like that. Those are basically types of process that happens during the training, and the model basically saves some sort of like a constant from training data into the graph. So the graph, the final graph that you have, that standard deviation, that mean, that quantiles, are generated from your training data embedded within the graph. So when test data comes through, those are set values. You're not recomputing those. Just the mean and the standard deviation of the quantiles. Test data goes through that mean, normalize it using the mean or the standard deviation from the training data, and goes for the it quantizes it. It applies the quantile to bucketizing it from the information that has from of your training data, and moves forward. So these analyzers are technically fixed and being computed over your training data. But there are other types of analyzers that you can use. This basically is summary of the same thing. These are like other types of analyzers. And analyzers, again, remember, these are types of operation that happens during the training. And it's fixed for your inference or testing time. Like scaling, bucketizing, vocabularies, like embedding, dimensional reduction. Those type of processes that you apply to the training data, you store that knowledge either as a graph, or you store it as some like a JLib or like a pickled model, and then you apply it to your test data. So these are again the process that you apply to your training. But if you work with something like TFP or just a graph concept, these are called analyzers. Now,
So question.
Yeah.
So the graph is the steps taking doing the whatever.
that's it. So if you again, I highly recommend you if you just simply go on Google search TensorBoard, there is already a Google Colab that you can just run it. It opens the TensorBoard to just show you that how you can see within a neural network. What will happen here is that if you think of, I have this one large neural network that data goes through, the TensorBoard basically tells you that, okay, on the first layer of the neural network, you have, like, let's say, 3 nodes. And then you have a bias. So basically it shows the data, how data goes through these and how the bias being added as sort of graph concept. And then basically, let's say you see after this, I'm doing some sort of like a normalization. Then the normalization will be like that. So you will need a mean and a standard deviation for that. So it tells you that normalization is going to be an analyzer. It's going to be fixed. You're going to learn it from the training data. And after you learned it, it will be an embedded fixed value, something that you cannot modify later inside your neural network. And when the new data comes through, you call to that number and say that, okay, I want to normalize it. Give me that mean, give me that standard deviation. Does that answer?
Yes.
So it will just change one time, you're saying, right?
So during the training, you will basically learn those information, those analyzers, and during inference, you basically utilize those. Again, think of these ones. How many you have worked with some of this probably, right? Have you worked with PCA before? Every time you apply PCA, you don't apply to basically, or if you use scikit-learn, during the training, you do fit train. During testing, you do predict, right? Because you already have learned it. For most of this, all of this, TF, IDF, all of this, those are the processes that you fit to your training data and apply it to your test data. And after you basically learn. Now, you can think of this. Let's say I had a pipeline, and as part of my pipeline, I needed to call to scikit-learn and do some PCA, and then I needed to call to scikit-learn and do some bag of words. And all of these were components, individual, separate from each other, outside of the model, right? But now you can do the same thing within a neural network. As part of your neural network, you can do PCA, bag of words, and actually you have way more these days, so it's kind of like the older image. But you can just embed all of that in one model, so you don't need to have multiple components. Because if you do a PCA, for example, after you trained it, you need to save it, and you need to load the data. If you have a bag of words, you need to save it and you need to load it. But if it's embedded as part of your model, it makes the latency of the process a bit basically longer, but then you don't need to worry about loading this, what's the version of the pipeline, the scikit-learn, what's the version of this, or all those issues that you could have in production. And mix all of those in one. All right, so now the other thing we have taught, we just specifically named it, was a feature space. We have been saying that talk about feature space and how that the data that you have is always should cover the entire feature space that you're hoping basically to address. Now, feature space basically in a 1D becomes a vector, right? As soon as you go to 2D, it becomes like that, 3D becomes like that, right? The more dimension you have, basically, the more complex this feature space gets, and the further the points technically become from each other. Now, think about a problem like this. So you're hoping to solve a simple classification on the left, where you're like, that's an ideal scenario. In reality, you technically get something like this, right? On the center. And if you have something like that, then you cannot solve it that easily. So, but your feature space at first might not help you, or might not be really good for the model that you have, but then you need to do some data manipulation. Most of the time, this data manipulation means that you need to increase maybe from 2D to go to 3D or 4 or more, basically. So you increase the dimension of your data, or basically you increase the basically a space that you need to cover. And that has its own problems we're going to talk about. Now, the main goal for your feature space is to ensure that the training and the validation data, or the training and the test data that you are targeting, they always have the same numerical ranges. Again, a simple example is that if you are targeting age group between this to this, during the inference, you cannot have outside of that age group. If you see something like that, you need to have a bigger conversation or change your scoping and say that, okay, you know what? Now we have a new age group. We either should reject them, or we should make a change and say that, okay, we're going to update the schema and accept this new age group. Because otherwise, if you don't do that, your model will basically produce unexpected result because it hasn't seen that type of data. It's not expecting that basically characteristics. It should be same classes. That means if you are predicting, I don't know, a cat versus dog, the user comes and uploads a photo of the bird, you know, it's not going to be same class. So you either need to ensure that you are focused on certain things, like we only do this 2 class, or you basically need to have a better scoping idea, like okay, you know, over time we can basically extend it to different classes. Similar characteristics for image data. That means if you have images that during the training, your images, they all have certain resolution, certain brightness. But during inference, customer comes and they upload images with a lower quality, lower resolutions. Instead of accepting it, maybe as part of the uploading process, you detect the resolution and stuff, and you give a proper error to the customer and say, okay, this is a low quality image, you need to upload it better. Instead of you receiving it and processing it and maybe generating something wrong, you can just simply verify based on what you're expecting, what you're hoping for, and reject or process for. Similar vocabulary, syntax, and semantics for NLP. That's also the same thing. Like you're expecting the specific types of document, you only work with that type of document. You know, so it's just you need to be sure that you're covering the space that you're hoping to work. Now, also you always need to remember that your data will be affected by seasonality. So you need to account for seasonality, trend, and drifts. During the serving, you will have new values and new labels that will appear. That's we will talk about that also today. That if new data types comes or new classes come, what should we do? How could we update our schema to account for changes instead of just throwing error at everyone? Because they're like, oh, we haven't seen this, or it doesn't work. Maybe we can update in the backends in a way that you accept the data from user, at the same time you're also learning from it. You know, it's kind of like a scenario level. And at the end, continuous monitoring is always the key for your success. Now, so that's just a feature space. You need to be sure that you cover as much as possible with respect to the project that you have or the product that you're building. But the next thing is like a feature selection, which all of you have done this before. The whole idea is that I have lots of features or I've built a set of new features. Now, among those, I need to select the most useful features. The type of features that, it's kind of like relevant to the task that they have. They carry the best signal, right? Now, one of the main reasons that you basically do feature selection from system perspective is I/O and basically to reduce the storage. I/O means input output, right? So it's kind of like the reading time from your system or basically writing time. You want to basically reduce that. You also want to reduce the storage. So if something is not necessary, from the system perspective, you can eliminate. Also, it will reduce the training time and the cost that you need for it. The more dimension that you have is by default, the longer the inference time and the higher the cost. So if it's not necessary, if it's possible, as much as possible to reduce the dimension. Now, when it comes to feature selections, there are two types, basically two categories: unsupervised, supervised, right? So we're going to see that how many of this type or different methods you guys are aware of. So whenever you do unsupervised, that means you don't have a label, correct? So when you don't have a label, what do you do? How do you decide which features to keep?
PCA.
But PCA is technically not feature selection. It's a transformation that you apply to the correlation. Okay, but correlation with among what?
We assign them we predefine features.
So you say we predefine the features. What does that mean?
Based on like what we're trying to like. Oh, it's an unsupervised.
It's unsupervised. So the reason I say correlation doesn't work, basically, correlation among what? You don't have label. If you just say correlation among features, that doesn't tell you about the predictability of if this feature have signals.
So keep some values constant throughout, we can drop that because it might not add some value in the prediction.
So that's entropy. Entropy-based technique, right? Entropy basically means that if something is always 1, 1, 1, 1 or 0, 0, 0, it doesn't have any variation. If there's no variation, then we basically drop it. What else?
Clustering.
Clustering. Okay, so what does clustering tell you?
You allow a group to like settle based on a certain feature, and like if like one set of features common, like it will like, pull the other features like similar to it closer to each other.
Okay. All right, so go back to what you mentioned, who said the correlation. So now talk about the correlation between the features. Second point here, like how would you decide using correlation among features, among columns, to which one to keep, which one to drop?
Two features are highly correlated, we can keep one and drop.
Okay, so that's one idea, right? Okay, so we're going to iterate on this one. When it goes to supervised, that's now when you have the column, the label, right? You might say that, okay, it's much easier now because I can decide which features to select or keep or to drop. The idea is that if you have a label, you need to compare the relationship between your features and the label, and based on that, make a decision on which one to keep or which one to drop. Now, there are various of techniques that you can apply, especially when it comes to supervised. So first one is we're going to talk about what's called filter methods. Then we have wrapper methods, and then we have embedded methods. So three categories of techniques for feature selection that you apply if in the supervised techniques. You have probably seen model type belonging to these categories before. So let's just start with filter methods. any basically technique that's or basically approach, which is a statistical, it's like correlation-based univariate feature selections. Those are basically called filter methods. Okay, so when you do simply you do a correlation test between your features and the target, that's a filter method. So what would you do? Well, if you find correlated features that are like highly correlated, you as your friend said, that you just see they are redundant, I would drop one or two depending on how many you have. Now, there are popular techniques that you can use for correlation. One of them is Pearson. You all have heard probably Pearson, right? Okay, good. The other one is also like a univariate feature selection. Now let's just start with this filter method. So you have all of your features. You start with all the features. You select a subset that is like the best. You build the model upon that. You do performance analysis, right? And when it comes to something like a Pearson, for example, you have some features like a correlation. If it's positive or negative is good. If it's zero is bad. Now, what if the types of, what if I tell you that the types of data that you have and the goal that you have actually changes the types of correlation tests that you need to take? For example, Pearson correlation is only good if you have a linear relationship among your features. If your features are non-linear, Pearson is not a good technique. On the other end, you have Kendall-Tau rank, which is good if you have a monotonic, basically, relationship. Anyone knows what's a monotonic relationship in the data? If it's increasing, it's always increasing. If it's decreasing, it's always decreasing. So this is monotonic data. So if you have a data that's monotonic and nonlinear, instead of Pearson, go for Kendall-Tau. Then you have a Spearman rank correlation. That's also monotonic, but if it can apply to larger data. So Kendall-Tau basically requires a smaller samples. Also, something like this is not monotonic. If you have an increase, decrease at any time, so it's not going to be monotonic. Now, when it comes to univariate feature selections, there are these methods that like mutual information. We have mutual information, we have F-test, we have chi-square twist that you can basically use. Let's start with mutual information. Anyone can tell us what's mutual information? Let's start with entropy. What's an entropy? Randomness. Well, entropy of, let's say you have a X and you have Y, which is your label. What does entropy of X tells you?
Rate of change of X with respect to.
It tells you how much randomness I have in my column, in my feature, correct? You also have entropy of your label. How much basically change I have in my labels, if I look in my labels. Now, what about information gain or mutual information? Anyone has heard of that before?
We use mutual information for clustering to compare different clustering methods.
So, can you, like in a layman term, tell us what does it tell you?
Similarity.
Similarity. Okay, what else?
It tells us how much X varies the entropy of Y.
So think about this. You have a column like a Y, and it has certain entropy. Okay. Mutual information gain, basically tells you that how much reduction in the entropy of Y I will have if you give me information about X. How much reduction in entropy of one variable you will have if you give the information about the other one. So when you work with like a feature selection, that you want to use mutual information, you're looking at the entropy of your labels, and that means that the entropy, let's say you have three columns, and then they have this variational entropys. And you're as soon as you add, so you have this, sorry, this three, you have this label that has three categories. But as soon as you add a column X, which is the features, you basically you're giving them information. The idea of that could be if you have an image of a cat, is a cat. If you have an image of a cat, versus if you have a label cat. Okay. So label of a cat has a across all your data, the label has some entropy. How much reduction in that entropy you will get if you give me images of cats and tell me cats has ears like this? You give me information about that. So you look across the features that you have, columns that you have, and you look for features that they have the best like information shared basically with the label. That means if you keep those, the entropy of your labels goes down. And you get rid of features that they don't have any mutual information between them and the column or the labels. So that becomes the mutual information. Now, there is a let me write down something. If you so let's assume you have two types of input data, numerical and categorical. If you are trying to do something like a regression, you do classification, regression, classification. For this is as part of the this other methods techniques that you have. But basically, what you can use Pearson, you can use Spearsman, you can use ANOVA, and here you use value square and mutual information. So you can basically keep something like that in mind. If you're dealing with numerical, depending on if it's regression or is a classification, maybe use those versus those. And if it's categorical data, you also do something like that. Okay. Now, when you go to something like scikit-learn and stuff like that, they all have this select k-best, select percentile. There's like these functions for feature selection. And those functions, as part of the parameters that you select, they require you to decide on the statistical test that you want. And the statistical tests that you see are going to be this ones. So it's like a F regression, mutual regression, chi-squared, F classification, mutual information, and so on. But all the idea is that depending on what type of data that you have, you basically select which one that they will. You also have some auto method that basically can help you with that. Now, these are like a filter methods. On the other end, we have wrapper methods. And wrapper methods are techniques kind of like a forward elimination, backward elimination, or recursive feature selection, which probably you have worked with those before. So, and the idea of wrapper methods is that you have all the features, you pick a subset, develop a model, you check the performance, and you continue with that process. Now, if it's a forward selection, it's a greedy method. You pick one feature at the time and move forward. That means you pick one feature, you build a, like, let's say you have four columns, you test each one, build a model, and pick the one that's the best. And then you go to the second dimension, add a second dimension, build model, and continue. So that becomes the forward selection until you reach to some performance that it cannot be improved more further than. If you go to backward elimination, is reverse. You start with all the features and you go backward. And here the idea is that you keep, yes.
So what's the difference between, so what's the grid search, which we do in like, and while we're training a model in ML? We have a grid search as well, right? So what's the difference between?
So grid search is a search technique.
Alright.
So I need to go across, let's say, this is the space that I have. And I just search through. Okay, so that's how you search through that. Technique that you use for search.
But but in the grid search, don't we like provide the hyperparameters and all the features which we need to use?
Yeah,
And
but
then it
so
goes-
I need to go through this space and find the best set of parameters for my optimization. Okay, and that we will see this later. And there are different search technique that you can use. One of them is grid search, which technically is kind of like you go through everything and you compare every run and you decide which one. Every run is not just one parameter, it's a list of parameters that you use for the model.
Alright.
Okay, what we are talking here is not about, and that's for hyperparameter tuning. What we are talking here is about feature selection.
I see.
When I say it's a greedy method, that means it's a method similar to idea of grid search. It goes across all the features,
Alright,
and then it basically decide, okay, at the end what to keep. But it's not what you are referring to. That's for hyperparameter tuning.
got it.
So, in backward, basically, you basically start with all the features and you go one at a time, and until you basically you keep eliminating features until you get to the subset that you're like, okay, we are good. And the last one is basically recursive feature elimination, RFE, which the idea here is that you select a subset, build a model, like you review the performance, you rank the features, and this technique is only applicable if the model that you use can gives you a feature rank. Not all models can give you that. Like tree-based models, they can give you that, random forest stuff like that. But not like probably not that easy. You can have a neural network and do basically feature importance because they don't provide it. So you need to have a few types of model that gives you the feature importance. And you discard the least important features and you repeat again, develop again, look at the ranking, drop the one that's not important, and continue to live until you get to the point that you're like, okay, I have this full subset of features. So those are basically wrapper methods. On the other end, you have embedded methods. Embedded methods are techniques like L1 regularization and feature importance. So anyone can tell us how the L1 regularization works?
If the values of parameters get way too perfect, we start penalizing the model for it.
So why it's the technique for feature selection?
So it utilizes the parameters with higher weights. So the
How does it help with feature selection?
So it reduces the weight by like to a minimal extent, which doesn't affect the prediction.
No, but those are all correct. But how does it do feature selection? It drops the weights to 0. When a feature has a weight of 0, it's not part of the model anymore, right? So that's basically that's going to be an embedded method. And feature importance again basically is the idea of like assigning a score to the features during the iteration. So basically L1 regularization, it does that. That's the idea. So you basically has some feature importance. So instead, okay, this is an important feature, this is not an important feature, and over time you basically drop some features. And this is like an example of scikit-learn, and you can see the feature importance like that. So we're not going to spend on this. All right. So let's move forward. Okay. So previous class, we talked about we talked a lot about labeling and why it's important. Most of the things that we talked about kind of was like a manual labeling. So today we're going to talk about some advanced labelings, and we start with semi-supervised one. Then we go to active learning and weak supervision. So why advanced labeling is important? Because you have lots of unlabeled data in reality. You want to build some basically some modeling or some product on top of that for business perspective. You also need to ensure that you have enough new data labeled for your pipeline to retrain and continue the process, right? So that's most of the time it's not possible to do that manually. That's why you want to do some advanced labeling or basically some other techniques. On have you guys worked with semi-supervised or heard of semi-supervised before? Right. Yeah. So let's assume you have this small amount of data labeled. That's all you could afford. Like for your company, for your startup, you had certain amount of money and you went just labeled that amount of data, the colorful. But you also have a large amount of unlabeled data. The idea is that, okay, how could I transfer that knowledge from that labeled data and apply it to unlabeled data that you have? That's the idea of semi-supervised basically techniques. Now, it has its own advantage and of course disadvantage also, but it basically helps you to unlabel a large amount of data in a kind of like a cheaper way. And it's basically somehow transfer that knowledge, depending on what algorithm also use the knowledge from the human or whoever has labeled it for you. But on the other end, we also have techniques called like label propagations. And label propagation is kind of like have you guys worked with Smooth? I know all of you have worked with Smooth. Smooth, yeah. Every semester, every student when they submit projects, they have applied the Smooth. It's kind of like by default. So what does a Smooth do?
Handles class imbalance.
How?
Like sampling.
So how does it build new data point? It builds new data point, right?
Statistical sampling.
What else?
By regional distance.
It's kind of like a neighborhood concept, right? So you look at the points that are basically minority, and based on this, the neighborhood that you are, between 2 points adds a new point. It's kind of like a regional or kind of like a structural concept. So in label propagation, we have some ideas similar to that. We use concept of similarity or community structure to label new data points. Now imagine on top, that's the data that you have, and those, the green, blue, and the red are the only one that you have labeled. The rest of it is unlabeled, basically. When you work with label propagation technique, and it's idea of like a graph-based one, you start with from where the red points are, basically, and the points that are closest to them, you basically start label them as red. As you get away from point, distance-based, if you see the basically the size of the size of the circles becomes smaller. Why it becomes smaller? Because those points you're less confident about the label, because they're closer to the red, but they're also close to blue. Right? So that's the idea of label propagation. So you start with some sample based on the similarities, that some structural concept that you have, you propagate through this and you do the labeling. Now, on the other end, we have a technique called active learning. Okay, so active learning, I think we previously talked about this, but the idea here is that we have data, and this is especially really useful when you have imbalanced concept, imbalanced data set. Active learning basically says that if you want to label data, don't just focus on labeling everything. There's some sort of like intelligent sampling and only label points that you are sure is going to improve or boost the model performance. Instead of labeling everything, focus on what is like the worst case for your model, something that you are sure if you improve that, it already boosts maybe the regional or the neighborhood of other points for your model. So it can be done by like a fully supervised or semi-supervised techniques for this active learning. But the idea will be something like this. So you have this unlabeled pool, and you have that active learning sampler. We're going to talk about different types of sampler now, which is going to be an intelligent sampling technique that large data comes and says, okay, from this data, I'm going to only pick this subset. That subset goes to some human labelers, or if you have some other pipeline for that, you label that, you train a model, review, and that loop continues. So it's kind of like a only subset what is more important. Now, the definition of important depends on what techniques you are going to use. If you use the techniques like margin sampling, in margin sampling, basically we say that label points that your current model is the least confident. Label points that the agreement between class 0 and 1 is really small. What does that mean? So if you look at the green line, okay, so that's your decision boundary. You have a classification. The two yellow points are close to the margin. When points are close to the margin, what does it mean? Your model is technically not sure. It could be class 1, it could be class 0. It just depends on where you draw that threshold. So because those are the points that your model is not sure, you swap, change the basically change the label and continue, see what will happen. You know, so it's the idea of like if the point was on the left side of the line, you basically tilt the line, bring it on the right side of the line, and see what will basically happen. And now next time, this one becomes the most uncertain point that you have. So that's one idea. The other one is, this is also related to margin sampling. This is a result from the paper of the margin sampling. So if they did a random training, it took 35,000 iteration, basically our training example, to reach to 84%. With margin sampling, after 5,000, they already reached to 8,000. Because after that 8,000, whatever data point you're using is not actually useful for the training. So it tells you that how it could boost up the your model training. Now you have also other technique that you can use in active learning instead of margin sampling. One of them is cluster-based sampling. You basically develop clusters over the space that you have, and based on that, decide which one to sample from. You could do query by committee. That means that you develop multiple models and you select data points that you have the highest disagreement among models. That means data points that all your models, let's say out of 9 models, 5 says class 1, 4 says class 0. Pick those points because those points are difficult for your model to learn, and try to label those ones up. And then you have region-based sampling. Basically, this idea is that instead of having one active learning, you run different active learning on different regions of the data. So the next one is going to be weak supervision. And this is what we saw in Snorkel. Right? The idea was that, okay, we have this large amount of data. How could we label it? The simple idea is that, well, if we have some domain knowledge in the lab that we had domain knowledge about definition of spam versus ham. So you're going to basically build those labeling functions, that's what we saw in the lab, the smaller functions. And you run those functions on some unlabeled data. Now, what will happen here is that, so let's say you have, let's say I built 10 functions. So I have basically 10 of these. So when you run this 10 over your entire data set, you basically get n by 10 if you have n data points. Every function gives you some value for the same data. So for every data point, you have 10 labels. Then that's where this generative model comes in. So the idea of generative model here is that you basically looking at these 10 values, which repeats across different data points, and you try to build a model that has lambda 1, W1, W2, W3, all the way through W10. And those W's are the weights of the generative model. Basically helps you that, okay, I trust this one more than this one, and so on and so on. So that becomes the way that this weak supervision types of model works. So you build this smaller function that from the domain knowledge that you have, then you build a model on top of that, gives some weights to the result of each model based on how accurate they were. Okay. So I've seen that. Now, the last part of the introduction, this one before the last, we have another thing. And it's called data augmentation, which the idea is that most of the time, if you're dealing with especially unstructured data, so yes.
So, the basic idea of generative and discriminative models are like we calculate like additional probability in one and joint probability in the other one. So how we are calculating weights rather than the probability?
So let's say, so we have a label here, right?
Yeah.
Okay. We want to define probability of y.
Like y given x, like
Yeah, so this is our x statement. So we want to calculate what's the probability of y given. This is the matrix that we have. So because this is generative.
Yeah.
In generative, this definition becomes probability of y times multiplication of probability of like this value, whatever it is, it's called lambda I given y, correct? So this becomes probability of one data point. Right? Now you want to develop a model for this. So you have n data points. So you basically want to calculate. I want a model that has a parameters by theta. So you want probability of my this parameterized by a theta. So you need to do it across all the data points that you have, ij from 1 to n. For every data point, this will repeat, but this is probability only for one class. That means if you have 4 types of class, correct? This becomes multiplication over I from 1 to 4. Then this will repeat probability of yij times this. Right. So now, what's the goal? Your goal is to find the theta. How do you find the theta? Argmax of this missing. You apply log on this, you do a transformation, and you just optimize it. So that becomes the generative idea. Now, in the discriminative part is after you have that, is you can swap the because this basically. Right, that's the only difference between generative and discriminative. Which one comes condition always? Okay. All right. Now, let's go on data augmentation. Who can tell us what do you think is data augmentation? What's your definition of data augmentation?
adding new data.
Let's go.
Create new data from existing data.
Create new data from existing data. Okay. Can you do data augmentation on a tabular data? So where could you do? Unstructured data. All right. Why couldn't we do it on tabular data? Because it just doesn't make sense. If you just simply build a new row, it doesn't have a meaning. It's a row, but it doesn't have any meaning. So why we could do it for unstructured data?
Because there is not the summarize.
No, because there are certain transformation that if you apply to unstructured data, it does not change the nature of the data. If you think of an audio of someone is playing guitar, you can increase like a bass on it or like increase, I don't know, I'm not good with music, but whatever of those knobs, is still the same music, unless you actually ruin it. Then that's not a good data augmentation, correct? So the idea of data augmentation is that you want to augment data. In this scenario, you basically flip the image. This is, from your model perspective, is a different image, but from the class perspective, it's like the same animal, right? So the idea of data augmentation is that any transformation that you can apply to your unstructured data, which does not ruin the concept of the data, is a value. What does that ruining it means that if you flip this, that's not a stop sign anymore. If you change the unstructured data and you put it in front of the human and they don't know what is this new data, that will be the same idea for your model, basically. Okay, so data augmentation should not basically be, it should be a valid augmentation. It should be something that it's not impacting the data itself. So some examples of augmentation. We're not going to go over this ones, but it's kind of like depending on the image, basically you just rotate, flip, and stuff like that. Add certain types of filtering theory. Now you for NLP on the other end, it's kind of like a harder to do augmentation. I personally have done some as part of some projects, but it's kind of like you need to be really like more careful, because the idea of augmentation in NLP could be like, you're like, okay, I'm going to swap certain types of words and replace those, but you need to ensure that the word that you inject or replace actually doesn't change the meaning of the sentence, because it's really easy to put a word, but it's when it comes as a whole, it changed the meaning of the sentence. So when you do data augmentation on NLP, you need to ensure that it does not change the subjectivity or sentiment of the sentence. So it's kind of like a bit trickier, but for images and audios are much easier, and videos are much easier to do data augmentation. But why do we do data augmentation? So we talked about it. Why do we do it? But why do you need, like, why do you need more data? Better generalization. Okay, so when do you think we will do data augmentation?
That's input point there.
Most of the time is when you don't have enough data, or if you have imbalanced data. It basically you do data augmentation. So this is the next question. Which part of your data set do you do augmentation on? How about your validation? You only do on your training data. Don't augment your validation or test data. That always should be the real data that you model being tested against. Okay, so all right. All right. So for the next part of the class, we're going to talk about data journey. We need to make the concept a little more exciting before we go for our guest speaker. Now, data journey is you're right now building a data pipeline, correct? Where are you standing in that? How many of you don't even know what to do yet? You all know what to do. There's a hand over there. All right. How many of you haven't started yet? So everyone has a start. Everyone is ready for submission. All right. So this is going to be important for you. So data journey, it's something that you need to always keep track of. It's and like across the industry, you always want to know what happens to data, what are the operations going on the data, where this data goes, where this data comes from, and so on. And that's the definition of data journey. And data journey basically it starts from raw features, some input output mapping to a model, and gives you some model. Would you believe if I tell you that a model itself it's a data, right? You agree with that? What do you think happens inside the model? We capture the relationship between features as part of the model, right? So the model itself is a transformation over the data that you have. So that's why it itself is a part of the data. Now, when the data transformation happens, it doesn't necessarily mean the process that goes over your model, over your data. Technically, it could be the input and output of your model itself. Like that's the data journey. So you need to understand that. You need to be sure that map it back and say that, okay, this was my data, went to the model, this came out of the model, why this came out. So you need to be able to trace that back. Now, in order to do that, you need to understand something called artifacts. Okay, and that's called now. At the beginning of the class, we said that we're going to talk about artifacts and ML, basically metadata. So artifacts, have you heard the term artifacts before? As part of the ML pipeline or software? Right, okay, so artifacts basically are any components, like any file, log that are being generated by your ML pipeline or data or by your entire pipeline. It's called artifact. Right. So if you go work in any company, and you're sitting with your other colleagues and so on, you hear the term artifacts, are basically means those components that are being generated and you store somewhere. Okay. Now, artifact basically could include the data, could include the log model itself. Those are all artifacts. Any input output, that becomes the artifact for you. Now, when you work with the this like artifact, this kind of thing. You build them upon your data, right? And we have talked about the data lineage and provenance before. Just again, to summarize, what was provenance? Where is this data coming from? What was lineage? The track of these things that is happening, right? So now, these two are pretty important for debugging purposes because it allows you, especially with the provenance, it allows you to say, okay, I had this data is here now, next time is here, what happened along the way, all right? So you need to be able to track that, and that happens through provenance and lineage. They also allow you to do something like a bug tracing or comparing the training runs. Like you have two training versions. In one version, the provenance is different because you did a different, maybe basically processes, so you did a different transformation, and you could simply compare those. Now, it's just a lineage. On the other end, lineage is kind of important for companies for protection, especially depending on where you are, which state, which country. You need to be responsible for the data, especially where, so lineage basically tells you that where this data goes, right? Provenance shows that who's this data is coming from and what's the operation basically all happen. Lineage basically focuses on if a user tells you to remove my data from your network, lineage will tell you where this data go to trace it back to remove it. So it's important for rules like GDPR and stuff like that, that it requires you to trace users' data back and eliminate. And you need to basically notify them within a certain number of days that we did that. You need to prove it, basically. So now, all of this requires some sort of like a data version. We haven't done the lab on it, but it's like one of the concepts here is DVC, data version control. Basically allows you to version the data on a different timestamp by building some sort of like a hash that you do comparison among those, right? If you do code versioning, you all have done GitHub. right? So if you want to do environment versioning, you work with something like Docker, Terraform, and similar. If you want to do basically data pipeline versioning, I think, or data pipeline versioning, you still can do something like what we did, Airflow. So it's going to give you a different version. So you have different components in your data, in your pipeline, in your entire product, and these components require different version tools. The most important one is the code versioning, environment versioning, and data versioning. When we will talk about also for experiment tracking, there are some like basic tools that these days you can use for experiment tracking and versioning of your experiments, which we will talk about those later. But all of this is going to help us to focus on ML metadata. So there is a library. We will focus on mainly with that because it's kind of like being used with TensorFlow, PyTorch. All of those are using the same library. It's a library called MLMD, ML metadata, basically, which what it does, it helps you to build metadata in your pipeline along the way and store that basically depending on which data storage that you have access to. So you will have a data pipeline, and this could be from your scoping all the way to your deployment, and it will create artifacts. When you have artifacts, you need some storage, right? You need some storage somewhere that you can store these artifacts, and that's the metadata basically that comes at the storage. Why do you need that? Because if you have built these artifacts, you should be able to also compare them among basically compare them like on the timeline. Let's say that, okay, what's the difference between this run we had today and the next run that we had like tomorrow? What changed between these two runs? Instead of trying to ask everyone, what did you change in the data and stuff like that? If you have proper basic artifacts and metadata, you should be able to just look at those changes. Now, in general, data validation, data transformation, all of those, is supposed to be some box around this metadata store. It's going to have some sort of like a storage that you will write. Let's just pick one example, TFX, that we saw the lab before. So on TFX has 3 components: driver, executor, publisher. If you look at through the code base that they have, that's basically what you will see. The job of the driver is to read the artifacts from your metadata store. So you have, when you work with TFX, under the hood, it has a metadata store that when the pipeline runs, it generates artifacts and metadata and it stores it somewhere. Okay. So when you want to, at some timeline or at a given point, you need to read some data from the metadata storage. That happens using a driver. And that's something that you don't touch unless you have a specific need. Those are like a predefined. But then you have executor. Executor is where your code goes in the TFX pipeline. So the driver is fixed. The executor is where you put your code, because that's where you already read something from the metadata storage, the data or whatever it is, and you want to process it. Then you have publisher. Publisher comes after the executor. So you already read the data, process it, did something with it, and you want to save it back into the storage. And that's basically where the publisher comes. And these are kind of like a similar concept that we're going to see also further. Now, any question on that? All right. So when we talk about this MLMD or ML metadata libraries, it helps you to track those metadata flow between different stages of your pipeline. And it also has a good support for different storage backend. You can do a local storage, you can do global, like a cloud storage. You can just, it's pretty resilient. When you want to work with MLMD, there are 3 main concepts that you need to learn: artifacts, execution, context. If you are an ML engineer, you will work with these 3. Okay, just take that. Artifact, execution, context. And then you normally have these data types: artifact type, execution type, context types. Then there is something called relationship. We're going to break this down. Relationship called event, attribution, and association. Now, what are this? So let's go here. Artifacts, as we said, is going to be any data that going into the model comes out of the model. That's always the artifact. Anything that you generate along the way becomes the artifact. Execution is that record of any execution, any code run. That's the execution. Right? You basically, it has a data type called execution type. Then you have context. Context is a conceptual grouping. How many times have you have seen this in Python or something? You use with this, and then you run something. Or when you work with something like Apache, you say Apache beam.context, open parentheses, and you run the rest of the code. Anytime you have something like this, that's kind of like an idea of grouping. What it means that anything that happens within this context is grouped under this. That means you can query that later. You can basically relate them together. You know, you can basically map those together. So in the idea here, in this scenario, you can look at the relationship in this way. On top, what you are seeing is the entire TFX pipeline. We don't care about what's on top. But on the bottom, the green box, basically tells you that the Google TFX, they built it upon this metadata storage. And this metadata storage has three main components. It has the artifacts with the data type called artifact type, that means anything that happens in that pipeline above, any input output will be stored as that data type, artifact type. Then it has execution and execution type. That means when the code runs, it needs to basically create some tracking of this code run, like what happened. And that basically is an execution type. And then it has a context. Now, context is, again, will be grouping over these two. So we mentioned that there is a definition called event. Relationship was event in the table here. So you see relationship, event, attribution, association. Event is the relationship between artifact and execution. When a code runs, it's a simple idea, is an event. So that becomes the event. Then the artifact is an attribute of the context. So context is a overall grouping. Whatever built up within the artifacts you make within this grouping, or basically cluster, is an attribute of this. Then you have association. The actual code that you run, or different codes that you run, are associated with this basically context. So it's like the idea is like it's kind of like a layman term, it's easier to follow. But you always see these three terminology in the pipelines, especially if you write your own pipelines, if you're not working with libraries. So again, event, artifact, execution, context. Now, the other benefit of a library like MLMD is that by default, it produces a DAG for you. Okay, so it basically converts that pipeline that you have into a DAG form. It allows you to verify the input by looking at the schemas and stuff like that. It gives you a list of all the artifacts that you can query against those. And also it allows you to compare artifacts, compare different runs, and basically see that what changed between those and what are the results. And you have seen this when we work with TFX. You saw those dashboards that you could see, or those protobufs that it created as the artifacts. Those are basically the same thing. Okay, so any question on artifacts or MLMD? No? All right. So the next thing is going to be evolving data. Did I hear something? Evolving data and a schema development. So previously we have talked about the schemas, and what did we say? Every time you have a data, you need to build a schema upon it. And when the new data comes, you need to compare it with this schema. If it's not the data that you expect, you need to do something about it. But what do you need to do about it if there is a update or new data comes through that I'm not expecting? And that's where the evolving data idea comes through. In reality, what data that you see in the industry or outside after you deploy is always going to be different from what you expect. So you are not going to have a clean deployment and say, okay, I deployed it, and all the data is going to have the same schema. No, and that's kind of like a dream. Most of the time, it's like you see some data similar to yours, and as soon as it goes out, all the bad data comes through. Now, what happens when something like that, basically when we have an event like that, that the new data types come, the new label comes through? What should we do about that? So we have talked about a schema, which just could carry different input, different features about your data. But then also, the benefit of a schema is that it helps you to find data skew, it helps you find anomalies. But if we find those, what should we do now? What would you do? And right now you're all building a data pipeline, right? So what do you do? What's that if statement that you put in your pipeline?
First, check the data.
And what would you do? Let's say you check it and you found something. What would you do?
If there is meaningful anomalies or meaningful skewness, go across the first step. And if it is really skewed, and if it was really an anomaly, we should eliminate or like reconsider.
By eliminate, you mean you reject that request, basically. What other teams they did? I can see lots of teams they haven't thought that far. All right, so you need to do a schema validation as part of your data pipeline, right? And then and you need to have an idea of like, okay, if something was bad, what do I with it? Now, should I just reject it? Should I store it somewhere, come back to it later? Should I update my schema? So that's what basically we're talking here. So what is really important, and why do we care about the schema and updating the schema? Because when you build a piece of software or platform, right, it should be reliable. It should work. It shouldn't break basically that easily. And that reliably means that, well, you receive inconsistent data almost all the time. It should be able to handle inconsistent data. Otherwise, you are constantly getting tickets or like, okay, it doesn't work. And software cannot be like that, right? So you need to be sure that you can handle inconsistent data. It should handle software issues, like any errors that happens maybe from a bad updates or bad software issues. It shouldn't just that easily break it down. User configuration, execution environment, any changes like that. So your platform should be reliable to changes or to bad data that you receive from all of this. On the other end, your platform should be scalable. Now, what does that mean? You could have high data volume during traffic, so it should scale with respect to that. It also should basically be able to answer to variable request traffic. Who knows what's the scaling mean in the deployment?
Does it mean like increase the number of workers based on how many requests we get and stuff?
Okay, that's right. What else? So scaling means that if I have lots of traffic right now, and let's say I have one GPU, because I was accounting that I have, I don't know, like 160 students, and you just need one GPU. But it's close to the exam time, and now everyone is basically making a call to whatever it is that one GPU does. So what will happen? It will go down. And if it's a Kubernetes or something, all those nodes, and we will talk about those later, they will just basically fail. So the idea of scaling is that if the traffic is high, we need to add another GPU. Now there are different types of scaling we will talk about. It's kind of like you do vertical, you do horizontal, basically. But for now, let's assume you just add another GPU and you split the traffic. The scale up. The scaling down also it needs to happen. That means as soon as the traffic went down, your pipeline, your platform should get rid of that GPU, extra GPU, because you don't want to pay for it. So you need to have a scalable, basically platform. This can basically respond to different traffics. Now, on the other end, when you deal with anomaly detection, you need to be sure that your pipeline can easily detect bad data. Compared with the schema, compared with the statistics that you have, but you need to have a test. You need to have a test say, okay, this is anomaly or this is not anomaly. Then it's really important. You need to treat the data errors as first-class citizen. Again, in software, code is the first-class citizen. In ML, data is the first-class citizen. When you find data error, treat it as a bug. Don't just say it's a data error. You need to create a bug ticket for it. Okay, because it's actually something that your model is built upon that. So if your data is bad, it technically means that your code is bad. And then you need to update your schema. And now the update your schema basically means that new data type comes through, new class comes through. Instead of rejecting it, make a decision. Maybe you have a pipeline that says, okay, if we saw 10% of the same new data that we are not expecting, then we're going to update the schema and we're going to do, I don't know, retraining or some way of accepting that data. Instead of rejecting 10% of the new customers, you want to basically accept those. So you need to be sure that you update the data schema that you're on. Now, when you are looking at the data, basically schemas, you need to also do a version tracking. Okay, I'm going to talk about why. Because simple answer, if you have a schema which is changing across time, you need to track it. So you need a schema version, like a version control. Now, when it comes to evolving data, you could also deal with different schema per environments. And that's where lots of time actually happens is you have customers, actually today I was on a call that this was one of the problem that we have customer that same data concept, different data format, right? As long as we convert the data, the rest of the pipeline works. But data need to become in that exact format that you want, right? So you basically, your entire pipeline is the same thing, but the schema that you expect is going to vary across different customers. Okay, so that's basically where you're going to end up with different version of the schema, and you need a version control. You also need, as part of the version control, to be able to swap different schema depending on where the traffic comes from. So that's basically the same thing.
Do we have different models for these different schemas?
So different schema doesn't necessarily mean different data. So let's say I'm just going to give you an example. What we do, we digitize manufacturing data as part of some review. And customer comes, uploads a PDF, and we convert that to manufacturing basically plan. Now another customer comes and says, I don't give you a PDF. Actually, I'm going to give you XML that contains the PDF data. Right? So the pipeline the model is the same thing, but the data comes in the different formats. So the schema, if you have a schema that verifies, did I receive this field? Did I receive this type of document? That check will fail because you receive different types of data. Right? But if you're dealing with an environment that the types of data or like fields, everything is different, then you don't have a same product. Like you're going to end up with variational product across different customer, which you don't want to do that because that becomes kind of more like consulting. You built one model for each customer.
So it will come in early in the pipeline, right? So basically your model is still being fed with the same schema, but in case it was different, you just extracted the same schema.
So you can think of kind of like you have an adapter that different schema comes through different data and basically unified in one and then goes through the rest of your pipeline. All right. So this is something that we saw in the previous class that, okay, if you have an anomaly, different types of anomaly could come through, like could be from a statistic, could be a schema, basically could be some values that's unexpected. So you can basically change your schema, that's the lab that we saw on TFX, to accept or to reject that new data type. So all of this is kind of like a schema and everything like that. It's something that you needed to build. Could be simple, could be more complex. Don't make it complex while you're building your product. Be sure that you have a fixed schema, fixed test, and a decision of when there's an anomaly, what would you do? Create an alert, create a ticket for it, create a bug, accept it, send the error, like graceful error to a user, say no or no. So all your decision. You don't need to do all. Just decide on which one you want to do. Now, so the next part is when we're going to talk about data storage. All right, we're going to start with something called feature store. Who knows what's feature store? Have you heard of feature store? No? All right, so think of this. You are working, let's say, all of you, like every student in this class, working on the same product. And as part of this product, let's make it. Let's say you're all working on the same data set, different products. Okay. Now, and you're belonging to the same class, so you are good to share information with each other. So one student comes say that I did a study, I found out this feature, I built this new feature is really good for this data set. So what happened here is that if that the student doesn't add that knowledge about these features, who created, why created, as part of which project, and so on, no one else might know about it, and everyone else might do the same thing. So the idea of feature store is that you have this central repository that you add features that you are sure is okay. This is a good feature. We need it for this data set or for this task that we do, and it's being pre-computed. We're adding it here. Now, later, some other team in a company, basically in a different part of the company, they're working on similar something else, not same product, but they need similar data. They can simply go to this feature store, look at pre-computed, pre-built features, and you can also see who has created. If you have a question, reach out to them, but utilize them. So instead of everyone just building all sorts of features, you can basically share that knowledge. So that's the idea of the features. So you can basically share and this knowledge and reuse that data. Now, it has some benefits. It's avoid duplication. If features are the same, you don't really create the same thing. It has a control access. That means it requires certain access level to access it. It allows you for purging feature or something if it's not important. It works in an offline manner, so it doesn't need to always be online access. You can actually work with it as an offline way. But the other benefit it has a low latency to accessing to features. When certain features are difficult to compute online, basically that means right away you pre-compute them in a different way, and then you store them into that feature store that could be utilized by another team. Think of this idea. You want to go on an Uber and you want to order an Uber, all right? Or you want to order food from many of these like a delivery app. And when you want to order, they don't need to wait for you to order to have knowledge about traffic, weather, routes, hours, and stuff like that, right? Because already they know it around the region that you are. So those are pre-computed features stored somewhere. So when you put a request, the only difference will be that from where to where, or from where you are ordering. And quickly they can just read from the feature store the other values that are pre-computed and just basically use that. So instead of basically generate everything online, you already have things that are being generated and stored somewhere. and you can just read from those because I don't need to do it like in an online way. It just need to be there. So that's one idea of the feature store. Basically, it helps you with some of this data generation. Now, it also allows you for batching, which is not that important part of it. Okay, so the next one is called data warehouse. You have heard of this one, probably, right? What do you call as a data warehouse?
Central repository where you have all data coming in from different sources.
Data comes from different sources in data warehouse. Anyone else? So data comes from different sources. What does that mean?
So it could be in different formats as well, but like, before it ends up in the data warehouse, it has to go.
Before it ends up in data warehouse, need to be,
It needs to be, it needs to follow the same schema, basically.
it need to be normalized. So data warehouse is basically some also central repository that all the data that goes through, they need to follow the same schema. So if your data has the same schema for storage, you can dump it into the data warehouse. It can come from different data sources. You process and analyze it and store it somewhere. So it's pre-processed basically. It read optimized. That means it's good for fast reading. Read optimized means that if you need a quick read, it's good. But it's not a real time because you need to do some pre-processing on this data. So it's not a real time data place. Okay. And it needs to follow schemas. It's basically has some key features. It's subject oriented. What does that mean? Subject oriented means that this data warehouse that we have is about customer. This data warehouse we have is about product, like shoes. It cannot be mixed. So it should be subject oriented. It's integrated, non-volatile. That means you track of all the timestamps. Data comes, you don't overwrite data. If you see a same shoe today and you see it tomorrow, you don't overwrite it. Basically, you just say that today versus tomorrow. So you can basically access different time variants. All right. So on the other end, basically, it for same thing for data warehouse. It helps you with some data analytics because it pre-processes the data, so it allows you to do these queries for some certain analysis. Timely access to the data, that means again, you can see all the time version of the same data. It enhances the data quality. Why? Because you pre-process, you ensure all the data has same format. So it enhances data quality. The study says it has a high ROI. We're not sure about that. And it basically increases the query and system performance. Now, what's the difference between data warehouse and database? The main difference, start at top. Data warehouse is online analytic process. When you try to do data analytic, that's data warehouse. Database is online transactional processes. Okay. Database is available real time. Data warehouse is not available real time. Database stores current data. Data warehouse, it has time variant data. Okay. Database size gigabytes. Warehouse can go to terabyte. Databases normally queries are simple, but data warehouse is not simple query because it's meant for analytics. So you need to actually write those queries properly. Database execution is in real time. Data warehouse is not real time. It's a long running job. It's kind of like a back job. So you write a query and it takes a while for you to receive that data. In warehouse, data does not do not need to be normalized. In database, they always normalize for efficiency. Okay. So if you want to think about the difference between these two, or which one should I use, depending on which one of these applies to you. On the other end, you have data lakes. Okay. So data lake is something that most of the time, me, you, our like ML engineers, I don't know, like AI engineers, data scientists, most of them we work with data lakes. Why? Because data lakes is where you dump all the data that you are not sure what you want to do with. You know you have this data, you want to build something on it later, but not right now. So you just need to store it somewhere, either in a compressed form or something. That's where the data lake comes through. Okay, so data does not need to be same format. It could be video, audio, text, whatever. You just need to store it somewhere. An idea of that could be if you think about the bucket on GCP. Build the bucket and you dump different data types in it, and you can later go extract this.
The data warehouse is on top of lakes then, because you cannot like directly query from the data, right?
So you cannot query from the data lakes. It's kind of like a storage. So you can access and download the data, kind of like a blob form, depending on which platform you're using, but it's not a query-based storage, because the data is not being stored as like some sort of like with some sort of query language. Okay. So now data warehouse versus data lake, processed raw data currently in use, not determined yet. Business professional, data scientists, costly to changes, it's highly accessible. You can just dump the data over there. So if you're working on something and you're part of your product, you're not sure what database I need to use, I'm not sure what do I do with this data yet, or for your log, just dump it in somewhere that later you can access. You can normally have some retention policy also that, hey, after 2 years, if I didn't touch this data, I start eliminating data to reduce cost basically. And the last one is the vector store, and that's basically where it comes to your LLM product. So it's like a different types of storage. The idea here is that you want some storage that could store high dimensional data, and you can basically query against those and like in some sort of like a fast way and accurate way. Okay. So in the idea of just, I'm not going to stand on this because I know all of you are doing the same thing probably. You have doing some document ingestion, you embedded a storage somewhere at query, you basically need to create embedding, search it through this vector storage that you have and extract some data. But yeah, like the types of these vector databases like a Face, Pinecone, Vivid, Chromo, and so on. It's like all has different aspects to this. Face is pretty much like a local on your machine. But Pinecone is kind of, I think the other one, Pinecone, you need to pay for its certain services and stuff like that. All the important part for you is that when you try to decide on your vector store is to be sure that it's scalable, can handle lots of queries that you have. Types of index type, flat, HNSV, IVF, PQ, or stuff like that. Those are different basically indexing type. This models, this type, this storages uses, and the difference between them is between speed and accuracy, basically. You know, it's kind of like a flat foot is like a greedy approach. You kind of, when you have a query, that embedding searches against everything to select one, but then the other ones you try to optimize that search, and basically you lose some accuracy or some recall basically to gain efficiency. You need to account for filtering. Basically, filtering means that it shouldn't just be embedding based. It should also do embedding and metadata based. You know, you can do a hybrid approach. It should have a good latency and the freshness. Basically, that means that if you need, can you add a new data or can you remove some data? So if you're deciding on vector store, those are the concepts that to keep in mind for yourself to just to see like which one is better for you. And this is just a table for the comparison among those. All right, so we're going to